Vision-based object classification from 2D image for mixed palletization in automated warehouse environment. The presentation is divided into 6 different sections: problem statement, method overview, method description, experiment and results, and lastly, conclusion and future work. In a typical warehouse, incoming items are placed on pallets, which are then stored on racks. This is a very labor intensive task. Modern warehouses store items of multiple categories. The process of stacking items of different dimensions on a pallet is referred to as mixed palletizing. For automating mixed palletization, the robot needs to classify incoming items based on their dimensions and place them according to a pre-computed palletizing pattern. The objective of this research is to develop a vision-based system to classify objects on the basis of their size for mixed palletization. Figure 3 shows how a typical pallet in warehouses looks like. Here we present an overview of the method. The assumption made by the proposed method is that the coordinates of the camera are fixed and the objects are placed against a contrasting background. The proposed method could be divided into 3 steps: background removal step, object boundary extraction step, and real dimensions calculation step. Figure 4 shows a process flow diagram for the proposed method. The input image is converted into HSV color space and color thresholding is performed to remove the background from the image. Then Gaussian blur is applied to smoothen the image. Adaptive thresholding followed by erosion is performed to extract the boundary of the object in the image. The contour created by the object boundary is found and a bounding box is drawn around this contour. Using the conversion factor calculated during calibration process, the real dimensions of the objects are calculated. Each of these steps are defined in greater detail in the following slides. A color space is a mathematical model describing a way to represent the color as a tuple of numbers. There are many popular color spaces such as RGB, HSV, YUV, etc. The input image is converted from RGB color space to HSV color space because in RGB color space the color and intensity information are mixed, which is not suitable for image segmentation. Image segmentation is a process of dividing an image into different regions based on certain criteria. Thresholding is one of the ways to perform image segmentation. Color thresholding divides the image into regions based on color information. In the proposed method, color thresholding is performed in the method to extract the object from the background. During the calibration process, the range of HSV components belonging to the background is determined. A pixel is defined as a part of an object if its 3 HSV components not all lie within this range. The thresholding operation is formally described in equation 1. Figure 7 shows the result of color thresholding on the image. The original image is shown on the left hand side and the final image on the right. In the final image, we can see that the color thresholding has effectively removed the background from the image. Gaussian blurring is a procedure to blur images and remove noise. It involves convoluting an image with a Gaussian kernel. The Gaussian kernel coefficients are sampled from the 2D Gaussian function. A 5x5 Gaussian kernel with sigma equals 1.1 was used in this method. Figure 8 shows a plot of the Gaussian function used to generate the kernel. Figure 9 shows the effect of Gaussian blurring on an image. Unlike regular thresholding, which uses a global threshold value, adaptive thresholding uses a different threshold value for each pixel in the image. This threshold value can be calculated in multiple ways. The method utilizes the Gaussian weighted mean of the 11 cross 11 region around the pixel location to calculate the thresholding value for each pixel. A constant number c equals to 2 was subtracted from the weighted mean to obtain the threshold value. Equation 3 and 4 formally describe this adaptive thresholding operation. Figure 10 shows the result of the adaptive thresholding. The middle image is the input to the adaptive thresholding operation, and the rightmost image is the output of the operation. The object boundary is extracted using adaptive thresholding. Erosion is a morphological operation in which a kernel is scanned over the image. The minimum pixel value overlapped by the kernel is computed, and the image pixel under the anchor point is replaced with this minimal value. The method utilizes a 3x3 matrix of all ones as the kernel. Figure 12 shows an example of the erosion process on a grayscale image. Figure 11 shows the result of erosion. The middle image is the input to the erosion operation, and the rightmost image is the resulting image after the application of the erosion operation. Contours are curves joining all the continuous points along the boundary having the same color or intensity. Contours provide information about the shape of the object. A rotated rectangle of minimum area, including all the points on the contour, was found. The sides of this rectangle were calculated. Figure 13 shows the contour created by the object boundary. Figure 14 shows a rectangle of minimum area including all the points on the contour. The real dimensions of the object, represented by R1 and R2, were calculated by multiplying the sides of the minimum area bounding box, represented by D1 and D2, with the conversion factor obtained during the calibration process. Conversion factor is the ratio of the distance of two points in the real world to the distance of the same 2 points in the image. Equation 5 and 6 depict this formally. The calibration process involves determining the range of HSV components of the background and the conversion factor, the ratio of the distance of 2 points in the real world and the distance of the same 2 points in the image. For determining the range of HSV components, an image without any object in it with only background was taken, and the minimum and the maximum value of all three components in the entire image was calculated. Figure 17 shows the histogram of all three HSV components in the background. For calculating the conversion factor, an object with known dimensions was taken. Using this method, the length of the sides of the rectangular bounding box of this object was calculated. Then the conversion factor was calculated as the ratio of the real dimension of the object and the dimensions of the bounding box. Equation 7 describes the conversion factor calculation formally. Three different experiments were performed to investigate the characteristics of the proposed method. The images for the experiments were taken from a 48 megapixel camera with GM1 sensor and f1.8 aperture lens in indoor conditions. The camera was mounted on a stand at a height of 40 cm and the objects were placed underneath it. All the experiments were performed on a computer with Intel Xeon CPU with Tesla K80 GPU and 12 GB of RAM. The proposed method was implemented in Python using OpenCV. Let's look at the first experiment. The method was evaluated on two different parameters. accuracy, and average percentage error. We define percentage error as the ratio of the absolute error in the prediction to true dimensions multiplied by 100. Average percentage error is defined as the mean of percentage error on all images of all objects. Accuracy as 100 minus the average percentage error. For each of the 5 objects, the following procedure was performed. First, the real dimensions of the objects were calculated to calculate the conversion factor. Then the algorithm was used to predict the dimensions on the 25 images of each object. The object-wise average percentage error in the prediction was noted. The result of the experiment is given in Table 1. The average percentage error in all 125 images was 6.492%. Among all the objects, when pen was used for calculating the conversion factor during calibration, the average percentage error in the prediction was minimum at 4.514%. When dot extruder was used for calculating the conversion factor, the average of the percentage error in all 125 images was at 12.063%, the maximum. This is likely resulted because of the large difference in the height of the extruder 55 mm and other objects. The mean height of other objects were 8.75 mm, which caused the extruder to appear bigger in the image than it actually was. Therefore, for the best results, the object with height closest to the mean of the height of all objects should be chosen for calculation. The prediction time is defined as the compute time or runtime that the method takes to make a prediction on an image. Average prediction time is defined as the mean of the prediction time on all images. The speed of the algorithm in frames per second is expressed as the inverse of the average prediction time. To calculate average prediction time, the algorithm was made to run on 125 images, 25 images per object, and for each object, the average time the algorithm took for prediction was noted. The algorithm roughly took the same time for all objects, around 4 milliseconds. The algorithm can be made to run at 250 frames per second. Another experiment was performed to evaluate the effects of the camera resolution on percentage error in prediction. The algorithm was made to run on 125 images, 25 images per object, at 5 different resolutions: 1000 into 750, 800 into 600, 600 into 450, 400 into 300, 200 into 150. The average percentage error at each resolution was noted down. The result of the experiment is given in Table 3. The average percentage error decreased with the increase in resolution, which can be understood by the fact that an increase in resolution accompanies an increase in the detail of the object in the image and allows for creation of more accurate bounding box. Here we list the advantages and disadvantages of the proposed method. The method requires no information other than the object's dimensions. Further, the method requires no changes to be made if the inventory changes. Both of these characteristics work in the favor of the method. The method suffers from few limitations, such as the requirement of contrasting background and calibration, poor performance in non-well-lit environments, and inability to distinguish between objects with the same dimensions. Here is our proposed method in action. A small data set consisting of 6 images is chosen for this demonstration. Let's look at those images. These 6 images were chosen for this demonstration. The name of the object present in each of these images are given above them, along with the dimensions of the object. So this image contains a Dobot pen holder. The dimensions of the Dobot pen holder are 144 millimeter cross 57 millimeter. This image contains a Dobot 3D printer extruder. The dimensions of the 3D printer extruder are 68 millimeter cross 51 millimeter. Now let's pass these images, and using our proposed method, let's try to predict the dimensions of the object inside them. So we have our predictions here. The predicted dimensions of Dobot pen holder are 148 millimeter cross 57.95 millimeters. So that is quite comparable to the true dimensions of the pen holder. Let's look at another example. The dimensions of the predicted dimensions of this objects are 68 millimeter cross 46 millimeter. The true dimensions are 65 millimeter cross 44 millimeter. So as you can see, our method has given a good approximation of the dimensions for each of these objects. In conclusion, a vision-based approach for calculating the dimensions of an object and classifying them from an image taken from a 2D camera for the purpose of automatic mixed palletization was presented. The algorithm had an error rate of 6.492% on average and ran at 250 frames per second, which makes it suitable for other real-time applications as well. The shortcoming of a few of the current methods, namely tedious calibration process and speed, were discussed. Shortcomings of the proposed method, namely the high error rate 14.76% when dealing with objects with a very diverse set of heights, was also discussed. In the future, work would be done to develop this method further for calculating 3D dimensions using multiple cameras. The method will be implemented on Dobot Magician, a robotic arm for practical training and education, for the purpose of experimentation, and will be adapted to solve other problems such as alignment and sorting of objects.